Hello, hello. Give me one. Hello, hello. Give me 1 second, everybody. Catching up ones. 1 second. I know someone's in the waiting room. I know. 1 second, 1 second. Okay, two people in the room. Coming and give me. Oh, people coming once. Hello. Yes, I haven't even said good. Yes, I'm going to say hello in a second. Sorry. Sorry, I know there's a delay. I'm delaying for no good reason. Well, yes, for a good reason. Well, a reason that's not. Hold on, coming, wait, there's still people coming. Uh, coming. What's the delay? I know. Good question. Oh, there's more people in the waiting room. I know. Uh, okay, what's happening? There's a million people in the waiting room. Okay, hello. This meeting is being transcribed. Okay. So first of all, hello, Vicky. Sorry about that. Hello, Gabriel. Sorry about that. Hello, Victoria. Hello, Sonam. Those are the visuals. The chat. Oh, more people. See, I'm late, but okay. Good afternoon, Victoria. That's a double right there. Good afternoon, Raina with the good afternoon. Good afternoon, Vicky with the double. Good afternoon, Gabriel with the double. Good afternoon, Mafine. Hello, Anthony. Good afternoon, Roger. Good afternoon, Sonam. Good afternoon, Melanie. Good afternoon, Zoe with the triple excitement. Good afternoon, Abid. People still entering. Good afternoon, Joel. Okay. All right. Hello. So, first of all, I hope you all, it's been a long time. I hope you all had an okay break. I hope you did have a break. One never knows with science students or science faculty whether there ever really is a break. I hope you had somewhat of one. I did. Thank you for asking. Oh my God. Sorry. I did. I also tried to catch up on work and do work for you, which I only to some extent succeeded. Let me tell you the status. This is part information, part apology. Um, I do have exams for many of you. I don't have exams for all of you. It's not personal at all. I tried to catch up this week. The exams are taking me a long time. I did do a lot of exams. In fact, I did a lot of exams. I have not finished all the exams. I don't even know if you can see in your the most of you in this section. If you turned your exam, again, this is not personal, but just as a matter of fact, you're not all getting them back today. So I'm not going to talk about them yet today. And I apologize. I was really hoping to have them all back today. I just don't. You still will get them back, um, in time for the final and all that. However, many of you in the room will be getting yours. If you can't, I don't know, you might even be able to already see it. And I don't want, but I don't want to spend today on it. So all the ones in this class, all the exams that I did that are ready to go, I'm going to like release right at the end of class because I don't want it to become I, I just don't want it to become like a big distraction or like a whatever. And because some people won't be getting them back today. Um, so the reality is, and again, it's not personal. I apologize. I'm just not done. So the reality is, if you turned your exam in on time, or early or whatever, then I think then I did those first. Just I did those first. So right when class is over, I'm going to hit the release button and then you'll get it back. Again, I don't know, maybe you can see it already anyway, but it'll be like the official score and everything will be released right. And I'm not trying to make this dramatic. Just the fact is, if you've been waiting for your exam, many of you will have it in an hour and 15 minutes. Some of you won't. That means you'll get it hopefully by the end of the week. I do travel on Tuesdays and Wednesdays, as you know, or Mondays and Tuesdays, so it's hard for me to do things when I travel. So I'm just updating you. So I apologize that not all of you are getting them back right away, but I'm moving through them. Obviously, and the more I get through, the faster the rest go. So anyway, um, so I apologize. Again, at the end of this class, a number of you will have yours back fully with the score and everything. And some of you, oh, hold on. Oh, okay, okay. Okay, so there's something in the direct chat. Which I will totally address in a moment. So, okay, look, I apologize. They are coming. They are not done. Many of them are. And please let's just like put it out of our mind, at least for the next 75 minutes. Then once everybody has them back, of course, like we can talk about them or not or whatever. But um um so that's on the exams. Now, as far as homework, um someone in direct chat just asked a question about homework seven. Homework seven, I think, is it homework seven? Homework seven is hard and big, but important. But it is definitely intense, and it's the last one. I think if it's homework seven, if it's what I think it is, the Gauss's law one. Sorry, I'm in the wrong. If homework so someone's asking me about homework seven in the chat. I believe that's yeah, yeah. So homework seven is Gauss's law, and it's so big and challenging and important that those fact and it's also the very last one. So and since I've not turned back your exams yet, I've already like 2 minutes before this class, I just postponed it. I apologize if you've already had stress around it. I certainly don't want that. So I've just changed the date so it's due a week from 2 days from now. The homework seven. Okay. And you everybody should have their exams back by then. Yeah, yeah. So we should all be caught with each other. And that's the last homework assignment. So yes, I'm going to help you with it for sure. I'm going to say a lot of things to me. It's very intimidating. It's certainly the hardest homework you will have had. I mean, especially if you look at it right now, if you understand what I'm saying. I will help with that a lot. I haven't said a lot that is helpful for it yet. I will start saying things that are helpful for it today and this Wednesday and next Monday. And next Wednesday. So hopefully that so to so to address the person in direct chat who just very reasonably asked about homework seven, my overall answer is I'm totally going to talk about it. I'm going to start talking about it today, but you have more time to do it than you might have thought, and I apologize for just making that change right now. But homework seven will not be due until a week from this Wednesday, in other words, April 30th. So hopefully that helps. Um, and again, until I get you what I owe you guys, okay, that's that. All right. Hopefully that answers. Okay. Could you just tell me the person who just wrote that in direct chat? Did I answer? Am I answering the question? Okay. All right. Thank you. No, I appreciate it. All right. All right. Good, good, good. And you get points for that. Okay. So now I want to go back to the material, which will I want to go back to the material of physics, which specifically is electrostatic fields. That's what we're talking about now. Yes. Okay. That's what we're talking about now. And um, I want to push the conversation forward. That my ultimate goal for today is to talk about field lines, which we haven't said anything about yet. We have talked about field vectors. Everything that we did on the class before break was about adding up the field vectors due to 2 point charges and getting one final field vector at some location in space. And that was like an involved calculation. I want to, but you'll notice that calculation was that super involved, even though all we were looking at was the field due to two dots. Like literally, all the work we just did last Wednesday, that prior homework, that was all about what would be the field, the electrostatic field, like over here at this location, due to two point charges, like one over here and one over there. Like, in other words, due to a proton and an electron or something. Like, and we had to do a lot of math just to get the field from that. Well, of course, the world involves a lot more than just like a proton or a electron. Like even the simple, even a drop of water contains a heck of a lot more than a proton and a electron. So there's got to be a way to think about the. There's got to be a way to analyze charge distributions and predict fields that can somehow give us a bigger, broader picture than just looking one pixel at a time. And that's the next topic. In other words, we're good. So and this is what homework 7 is all about. So sorry, my okay. What we want to deal. Oh, you can't even read my hand. I can't read my hand. How could you read my handwriting? Okay, what this says is what we're going to deal with now, what we're shifting our attention to now, is continuous charge distributions, source charges that aren't just one dot at a time, but might be but are continuous series of dots so close together that the space between the dots is infinitely divisible, right? So that you have like solid materials of charge, like a line of charge as you might find in a wire, or a plate of charge as you might find, like a sheet of charge, like you might find in something that's called a capacitor, or a ball of charge, like you might find in like a Van de Graaff generator or something. Okay, that's what we want to deal with now. Continuous charge distributions, excuse me. It's changing the okay. So we want to deal with continuous charge distributions now. Not just one dot at a time. Now, the principle behind everything we're about to do still is that the field from one dot will continue to be given by Coulomb's law, right? Which I'm badly writing right here. Like the field that one point source creates is still given by Coulomb's law. And the field created by more than one point is given by the sum of a bunch of Coulomb's laws. Like that's what we sort of believed and did last Wednesday. But now we're trying to, so what I'm believing is if I had a long line of charge and I wanted to know the field due to the line of charge, like the field over here, in principle, it'd be the field. In principle, I would think of that line as a sum of many dots, and each dot would create a field vector according to Coulomb's law, this thing that I just wrote down, right? And the sum of all of the Coulomb vectors would be one big resultant vector that would give me the field at some nearby location. But that's a lot of calculations to do and a lot of arrows to draw, right? So we're believing that field obeys superposition, that the whole is equal to the sum of its independent parts, but we're also now looking for a way to do sums more efficiently than everything we did last week or 2 weeks ago. So first, we're going to change the way we visualize. Let me remind you. Okay, I'm going to the same drawing that's on the front of the board today. So remember, let's say we have a positive. So what I'm going to change our visualization technique now, to adapt to more complicated situations. So remember, if you recall, if we have a point source, a positive source of electric field, in other words, a positive charge that's just sitting there plus Q, the way we think of the field that it produces, we think of vectors. Like a field really is a vector valued function. It says that for every given point in space that you can imagine, if you think of the points of space as the input, there's an output, which are field vectors. At every single point in space that you could consider, there is an arrow sitting there whose length represents the strength of the electric field and whose direction, whose tip to tail orientation represents the direction of the electric field. So the electric field vector or vector field representation from a positive source would look something like this. And this is a representation, right? Like in principle, there's an arrow at every single point in space you can imagine, but I've drawn just enough arrows to show the pattern. And what is that pattern? The pattern is that 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 first of all the arrows are pointing out along radial lines away from the positive point source. They're pointing out because the source is positive. Because what it's saying that like if you went to any given place, like right here, and asked what's the field doing there? Well, what you're asking is if I were a positive 1 Coulomb test charge that were sitting at that blue dot at that point in space, what would happen to me? Well, if you're, because the test charge is always, the test charge, right? When we're talking about fields, it's always positive 1 Coulomb of charge. So if you were a positive sitting there at that location of space, you would be pushed away by the positive source, right? And so you'd be pushed along a line connecting you to the source, but you'd be pushed out because you're positive and it's positive. And if you're, and the farther away you are, the less you'd be pushed, right? Inverse R squared law. So all the arrows point along radial lines out from the source and they get smaller and smaller, in a given rate, um, as you get farther and farther away. Right? So that would be the vector field representation from a positive source. Similarly, just to be clear, similarly, if it were a negative source, it'd be the same idea, but all of the arrows would point in. Wait, is this thing? Hold on. Why is it shaky? I'm the only person in the world with a. It's like they match the tablet's spasticity to the user. You know what I mean? Like, yeah, you get it. Okay. It's like if you want to know whether people are, whether creatures are the way they are because of nature or nurture. If you understand, that age-old question, like, are you the way you are because of your environment or because of genes? Well, all you have to do is look at people's dogs, and you know right away that it's nurture, not nature. Because like my family's dog is a complete spaz, totally neurotic, totally a freak show, and like our dog does not have our DNA. So I mean, like you be the judge. Okay, anyway, so this would be the the vector field representation from a negative charge. Same pattern that the arrows are getting smaller and smaller as you get farther and farther away, right? Because of inverse R squared. But all the arrows are now pointing in. Why? And I need to emphasize this. Maybe I just because I never got this right in college. This always what I didn't understand in college. I mean, or I didn't hear the 85 times they told me was the test charge is always assumed to be positive. When you're thinking about fields, you're thinking about what something would do to a positive recipient. There is no recipient. But you see what I'm saying? It's a field is a prediction of what would happen if positive 1 coulomb of test charge were sitting at a given location of space. So the test in our mind is always positive. The source could be positive or negative. So when the source is negative, as it is here, a source would pull in on a positive test. You see what I'm saying? I mean, stop me if you don't, but the test is always assumed to be positive, the receiver. Uh, but the source could be whatever the source is. So okay, you get the point. So, or if you don't, tell me. So the vectors representing field from a negative point source all point in. Now, what I've just drawn is a bunch of vectors that are just representation, that are just a sample of what the whole picture of field looks like from one dot. Now, look how many arrows I had to draw just to give you an idea of what the situation is from one dot. That's a lot of freaking arrows to draw from one dot. Can you imagine if we had more than one dot? If we had a couple of dots, well, that was last week, or if we had 3 dots or 4 or a line of dots, we'd be drawing arrows forever, right? So we have a different picture. We do this is still correct. There's nothing incorrect about this, and sometimes vectors are still very, very useful when you're talking about fields. However, there's when we're talking about continuous charge distributions, there's a more useful representation, and it's called field lines, not field vectors, field lines. To make field line diagrams, we sew up all the vectors like this. If you have a positive Q, so say a dot like a proton, right? Like just like before, but you want to depict the field from it using lines rather than field vectors. You connect up all the vectors along a given line. Yeah, you connect all the tails of all the vectors. So what you'd have is long lines, and then you shove the arrows into the middle of those lines. So you have something like that. And if you were doing, and if you do, and the negative, they'd be all pointing in. I'll draw that in a minute. Now, well, negative would be like this. Now, in the case of one dot, that doesn't look like a huge gain. I mean, still a bunch of lines to draw, but I mean, honestly, it cut down on a third. I mean, it just reduced the number of hours I drew to a third in the way that I did it. But it ends up being even a much bigger advantage with more complicated situations. So let's talk about this first. So now we have lines instead of arrows. These are no longer vectors. I'll tell you what I mean by that. These are now field lines. Um, well, all right, yeah. To give you an idea of field lines, I'm going to shift the screen here. I'm going to you could do this on your own as well. Hold on one sec. Okay, yeah. Okay, if you look at the screen now, all I did was type, well, as you can see, I typed E-field line diagrams into Google Images, and I get all this like stuff, right? All these drawings that are really cool, right? I'm going to focus in on a couple of them in a moment, but I want you to just get a sense, and you've probably seen these kind of images before, or and maybe in high school, like studied them. Um, These are field line diagrams, and these are for increasingly complicated cases. Even well, yeah, I mean, some of these cases are, more complicated than others, but I want you to just so ultimately, field line diagrams are what we use to handle sophisticated cases that are just more than a couple of dots. And ultimately, what we use to handle cases that may not be dots at all, but might be lines or plates or spheres, uh, like I said before. But I want you to notice a couple of things about these pictures. But first of all, they're cool, right? I think. But second of all, you notice that the lines can be curved. That's a huge point number one. In all of these pictures, the lines are all connected in a certain kind of a way, but they're curved often. And um, that tells you right away they're not vectors anymore. Um, and one of the reasons that we shove in most customs these days, we shove the arrow to the middle of the line is really to express the fact that this is not a vector. And when I say it's not a vector, what I specifically mean is we no longer use the length of the line to indicate magnitude. It's like a very different representation. from the vector representation. It still is a highly precise representation that can be used as a computational tool as long as you draw it to scale, just like vectors are not just rough sketches, but are computational tools as long as you draw them to scale. Same thing here. It's just it's going to be used in a different way. So first of all, notice that the lines they don't have length. They literally don't have length anymore of any significance. Whenever it looks like a line has length, like like um like even let's say this hello. Why did that not do what it oh, for heaven's sake. Well, okay. Even like this is probably a copyright infringement, I apologize. But like even if you look at something like that picture in the middle of the screen, some of the lines might look like they are ending and have a particular length. But if you once you get used to these things, you realize like no, 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 no. Even the lines that look like they're ending, they're only ending because they're hitting the end of the page. If you know what I'm saying, the page just ran. Oh, for heaven's sake, the page just ran out of room. And we're trying to get that across by putting the arrow tips like at arbitrary spots in the middle of the line. We're saying this line is going on forever. So there's no significance at all to the length that it has or that it seems to have. You follow me? So they can I'm going to write down these rules for you in a minute, but I want you to see that the lines can curve, they can bend, but they don't cross. They never cross, and they do. Okay, okay, we got the point. Okay, they don't bend. I mean, they do bend, they do curve, they don't cross, they don't end as such, or they certainly don't end or begin at arbitrary points on the page. There's one other thing I want to say about them, and then I'm going to give you the rules now. Well, also note, no matter how complicated the picture or cool or uncool the picture might look, like even like I'm afraid to I'm afraid to double click anything, especially something that says Reddit underneath it. But no matter how elaborate a picture might look, it always has some kind of pattern and smoothness to it, right? There's always an interplay of symmetry and asymmetry in these pictures, and that is not an accident or coincidence. That's the point. Um, so how do these lines work? Like, what are they telling us? Well, well, yeah, I'll go back to this. So, okay, I'm stopping the share. Stop the share. I'm gonna go back to the board. Hang on one second. Okay. Okay, here's what I want to say right now. Um, I'm trying to emphasize and repeat that these field lines are a new representation of an old quantity. Like the field lines are what we're going to use now to represent what field is doing. Like field lines on a piece of paper represent what field is doing in space. Now, field lines are meant to capture and convey the same information that field vector arrows were conveying. Field is a vector quantity. Field has magnitude and direction. So these lines are meant to convey magnitude and direction. Direction they convey the same way as vector arrows do. Like we still have little arrow heads that we stick in that show if a field line is going this way or that way. Um, but now the field lines can curve. So specifically, so it so if you want to know what direction the field is pointing somewhere in space, you would look at a field line picture or a field line diagram and find the location in that diagram that you're interested in. And whatever line you're closest to, the field pushes in or pulls in the direction that's tangent to the line that you're closest to. You follow what I'm saying? I mean, I don't want to overspeak it, but the lines can be curved now. So what's the direction of a curved line? What's the slope of a curved line at a point? Well, it's whatever the slope is of the line tangent to that curve at that point is. Just like calculus, just like derivatives and all of that, right? So direction is now given by tangent. You have to. I think you get what I'm saying. I mean, if so, when you want to know the direction of the field, you ask yourself what direction is the tangent line to the field line at that point, assuming that the field line itself might well be curved. That's direction. But basically, I'm saying you look at the arrows. Um, but now magnitude is a more interesting thing because with vectors, the length of a vector arrow indicates the magnitude of the vector quantity. But we no longer have lengths in these pictures anymore, is what I was trying to say before. So how do we infer or represent field strength? And the answer is density of lines. Specifically, and I mean the density of lines, like the number of lines per area in a given region of the page. So, like, even if you just look at this picture right here, and I'll go back to the Google thing possibly in a second, but if you look at the field from, well, okay, look at the field vector diagram from a point source. It's clear there, I hope, that as you get farther and farther away from the point source, the arrows get shorter and shorter, and that's what they're trying to say, those shorter and shorter arrows, is that the field is weaker and weaker as you get farther away from the charge. And why is it weaker? Because field is KQ over R squared. And the R is bigger as you get farther from the positive Q, right? But if you shift now to this picture, you don't, it's still got to be true. It's still true that as you're farther and farther from the positive Q, the field strength had better be weaker and weaker, and by the exact same amount. Like we're trying to convey the exact same information here. but we don't have arrows that are getting shorter anymore. So what do we have? Well, if you look at the picture, as you get farther and farther away from the positive Q, the lines are getting more spread out, right? There are fewer lines per square centimeter on the screen, like out here, than there are in there, right? And if we were drawing this diagram perfectly to scale, we could literally capture the numerical relationship with precision. What I'm trying to say is tighter lines, denser lines mean stronger field now, as opposed to longer lines. I'm saying denser lines. That's how you read, that's how you write and read field lines. Like again, I'll just really quickly, I think if I can do this, uh, I'll, yeah, I'll try to do this really quickly. Like if, where did it go? Yeah, if you just look at these pictures and any, like any one of these pictures, I don't know why I'm so afraid to double click, but like, yeah, like where the cursor is right now in this picture here, you see the lines are really, really close together, around this source right here. And then as you get farther and farther away, the lines are less and less dense. That means the field is getting weaker and weaker as we get farther away. It's stronger right there. And as the situations get more complicated, the regions of intense field and less intense field become, more interesting. But high density lines means strong field from now on. Okay. And you can stop me if that doesn't make sense. I'm going to stop it. Um, so now I want to get more specific about how you draw these lines. Okay. All right. So, like, literally, how are these diagrams made? They look very intimidating, or they can look very intimidating at first. Um, but they are, and they take a little getting used to, but they do follow strict rules. Um, so the rules are these. Okay, the first thing you do, whether you're literally doing this by hand or you're doing it into a computer program or software or something, or you're trying to read a diagram, the first thing to understand is that there's like a scaling factor going on where for every 1 coulomb of source charge or every Q of source charge, like it might be a number or it might be expressed as a variable, but for every given amount of charge, we're drawing a certain number of lines. I say eight. Eight is a reasonable, often is a reasonable convention because, like, if you literally just had one dot like this, it takes about 8 lines to give a sense of what the pattern is. right? So you pick a scaling factor, and then you're going to be consistent with that scaling factor throughout the whole diagram or throughout any other diagrams that are coming along with it, right? So it's a number of lines for every certain base amount of source charge. Then, once you've chosen the scaling factor, then you start drawing lines. And every field line you draw, every field line, sorry, we'll call this rule 2A, must either start at a positive or come in from infinity, which means off the page, right? Every single field line that you start, in other words, you never start field lines just spontaneously in space in the middle of the page. Every field line you start, so what you do is you start all your field lines from any positives that you have. And then every single field line, you can imagine where this is going, then every field line must either end at a negative or go out to infinity, which really means off the page. It means so I'm gonna go well, I'm gonna go back to those pictures in a second and show you what I mean. But so what this really means, so positives begin at I mean, all field lines, they begin at positive, they end at negative, or they go off to infinity or come in from infinity. What does that, I mean, what does that mean? Or what possibility am I ruling out? The possibility that we're ruling out by this rule is no field line will ever start or stop spontaneously in the middle of the page. If a field line looks like it's ending, that just means it's run off, it means the page is run out, or vice versa, right? That's what I'm trying to say. So all field lines go from positive to negative. Um, okay, I'll leave it at that for the moment. You'll see why the infinity thing is involved in a second. Then three, field lines can, as we said before, can bend or curve, but they cannot cross. Um, now why can they bend and curve? And well, the reason field lines can bend but they can't cross is what is a field line in the first place? It was a sewing up of a whole bunch of field vectors, right? So field lines are meant, again, I keep saying, are meant to convey the same information that field vector arrows were conveying, only they're conveying that information in a more efficient, in a more macro kind of way, right? So what we've done to create field lines is we've just looked at we're imagining that we had a big piece of paper that had a whole bunch of arrows on it, and we just sewed up all of the arrows um, that were going along particular paths. we connected all of the tails of all of the arrows together into one long line. So um, on the one hand, because we were connecting a bunch of arrows, the connection need not be straight, right? Like I'm getting myself tongue-tied, but because it's more than one arrow being connected together, there's no reason, because it's more than one arrow, there's no reason to believe that all arrows would point in the same direction. Hence, the line that's connecting all the arrows together might be curved. But the reason that the lines can't cross is that what we're connecting together are vector sums. Like all of that work we did last week was to add the vector from one point source to the vector from another point source and get one resulting vector arrow. The field lines are meant to indicate resultants. They're meant to indicate net, in other words, or I should say, the field lines indicate net effects of field vectors. So if ever there were two vectors that were crossing somehow, like from last week. If you are being pushed in one direction by one charge and you're also being pushed in a different direction by another charge, that would be two vectors that might look like they would cross each other. But you add them together to get a final vector, and that's what we're using in our minds to draw these field lines. So the field lines are already the effect of everything being crossed together and added up. I'm not saying this well at all, but the field lines are the net effect at the end of the day of all of the forces acting together. So they can't cross because that means you haven't finished doing the math yet if they cross. Okay, so that's rule number 3. And rule number 4, the final rule is at the end of the day, so so the whole field line procedure is you pick a scaling factor. You then start drawing lines from positives to negatives, and you draw the simplest, smoothest, most symmetric pattern of lines that you can without violating rules 1, 2, and 3, while allowing yourself to bend the lines but not cross them, and while making sure that you never have a line start or stop spontaneously in the middle of the page. You just draw the smoothest, simplest, most symmetric pattern of lines you can according to those first 3 rules, and that will be the field line picture. It takes a little while getting used to, but you'll find that there's one and only one way to draw any field line diagram once you're making sure to obey the first 3 rules. You'll know you've done it right. Okay, two things to check to notice about field line diagrams. One, and I'm going to go back and show you the Google images again so you can see all this like at once, but you'll know you're doing field line diagrams correctly if they start getting more and more uniform as you get farther and farther away on the page from whatever's causing them. Like the pattern will always be the most intricate, closest to the stuff that's causing them. And then as you get farther out, the lines will spread out and get closer and closer to just being a bunch of sort of parallel lines. That's number one. And number two, okay. Um, that says DIFF, which, well, okay. So what I'm trying to say here is field line diagrams will only be as asymmetric as their source distributions are. Again, I'm going to show you that. I'm going to go back to the pictures in a second so you can see what I mean. But I'm saying field line pictures will always have a certain amount of symmetry to them, just like recognizable gut level visual symmetry. And they'll always have some degree of asymmetry. The more symmetric the source that caused them, the more symmetric they will be. The more asymmetric the thing that caused them, the more asymmetric the patterns will be. In fact, specifically, and in a similar way, like what the field lines are really indicating is asymmetry. Like the whole purpose of a field line picture really is to show us where there are asymmetries in space being caused by asymmetric distributions of charge in space. What a field is, what the field, I mean, remember, the field is all about action at a distance. The whole idea of the field, whether it's the electrostatic field or the gravitational field over here in space is the information over here in space that's indicating an actual object that's over here in space, right? Like if there's nothing in space at all, if there's nothing in space at all, then there's no field in space. There's just empty space. Now the lower hand. Sorry. If if there's nothing in space, then space is pure and empty and it's purely symmetric, right? Space is homogeneous and isotropic. It's the same, like a cubic foot of space over here is indistinguishable from a cubic foot of space over here. And this direction, this way, is indistinguishable from this direction in pure space. Then you put an object in space, like a point of mass over here, or a point of charge, like a source charge, like a proton over here. Now, there's field lines everywhere in space. The field lines are information in space that indicate there's something going on somewhere. The field lines have a certain asymmetry that indicates the asymmetry that now exists in space. Space was purely the same everywhere in all ways before. Now there's a dot in it somewhere. It's just a dot, but that breaks up the symmetry. It means something over here is different from the emptiness over there. So now in space, there's a bunch of arrows coming out of that dot, if it's a proton, let's say. Now, again, not literally, I mean, I don't literally mean there's literally arrows in space, but there's information in space now everywhere. Everywhere in space now knows there's a dot over there. And a dot is pushing on space everywhere. It's pushing more here than it is over there. It's pushing in that direction over there. It's pushing in that direction over there, etc. So there's now a bunch of lines, at least in the way we imagine space. There's a bunch of lines in space. They have a certain amount of symmetry in that they're all radial, they're all pointing, they're all in a sort of a pattern, but they have a certain asymmetry in that they're all starting right over here. So the asymmetry of the lines indicates the asymmetry of what's actually going on. And it is through that asymmetry that the information of an actual object is conveyed to the rest of space. Field lines are the difference that make a difference. That's what it says in blue to the right. DIFF stands for difference. I just can't fit it there. Okay, so I'm going to go back to the diagrams again, just to try to show you what I mean. So this isn't quite so abstract. And it is pretty abstract, but hold on. Like, like a good example. Yeah, let me see if I can double click this. Oh, well, actually, that's not what I want. Sorry. Well, I mean, yeah, I mean, that is sort of an example. If is this the same one that's sorry? Okay. No wonder that. Okay, so look. This is a perfect example of what I'm saying right here. Like, if you first look below at the blue picture, you've that's a field line diagram from two. Uh, well, no, I mean, I don't know why the top. It's weird. Sorry, the top blue thing is a positive. I don't know why it has a negative sign there. Like all the lines are coming out of the top, so that's a positive. That's weird. Oh, it's saying the diagram is invalid. For God's sake. Okay. Uh, sorry. I'm trying to say, hopefully, if you just look at if you look at these pictures, like okay, that right there is a valid diagram of two positive charges, right? Like two positive sources. Notice each as you get farther and farther away from the charges, it what you're experiencing in the lines is the same thing that you would experience if you just had one positive source in the middle of the page, right? Like it's only as you get close to the two charges themselves that you start seeing funny business in the lines. Um, and I want it also to be clear, like the lines in that drawing are showing the same thing that the vector calculation from 2 weeks ago was trying to indicate. That is, this is not, if you just look at the picture in the middle of the page right now with the two red dots, I think it's the only picture in the page. Yeah. If you just look at that picture, that is not an indication of what one red dot is doing to the other. It is not. I believe someone in the class asked me about that in a direct chat last week. It's not an indication of how one charge is repelling the other. It is how are those two charges together affecting the rest of space, right? So for example, if you look at this point in space right here, what the lines are trying to indicate is what would happen to a +1 coulomb of test charge if it were located right here. And the answer is it would be pushed up, right? It would be pushed up. Why? Because from the left positive point source, the left one is pushing it up and to the right, while this one, the other one, is pushing it up and to the left. So the left and right components of the vectors cancel, and you're left with an arrow that's just pointing up, right? And your point, and so you'd be shoved up with a certain degree of strength, a pretty strong field because you're pretty close to the red charges here. But then as you get farther and farther away, the field would get weaker and weaker. You see what I'm saying? And if you were like right here in the center, the reason like there's barely any line there at all or any arrow telling you what would happen is one would shove you to the right, the other would shove you to the left. So you'd have a net force of like nothing and you would just sit there. You see what I'm saying? Okay. Um, so the pattern is not perfectly symmetric. It's exactly as symmetric as the original pattern of dots is, right? It's almost as the purest, most symmetric case would be nothing in space at all. And then we'd have perfect, like, then no one line would go any different from any other line. There'd be no lines at all. I'm not saying this. You see what I'm saying? But then as you get, this has a lot of symmetry, but is but is different because now this is the lines from a positive and a negative. And yeah, I want to say one last thing and then we'll. Yeah, okay. This is what I want to say. All right, but now the perfect example, I will end on this. This red situation right here in the middle of the page. You can tell that yes, the red dot to the left is positive and the red dot to the right is negative. You can tell because the lines are coming out of one and they're going into the other. But notice some lines are going off to infinity. This is like what I was talking about in the original rules. Some lines are going off to infinity. No lines are coming in from infinity, but some lines are going off to infinity. Why is that? Because there were, even though we have this rule that anything that starts has to start at a positive and anything that ends has to end at a negative, we actually had to draw more lines coming out from the left-hand dot than there are lines coming in to the right-hand dot. Why is that? Because the left-hand dot is more highly charged than the right-hand dot. Like this is two opposite but not equal charges. You can tell because there's a greater density of lines coming out of the positive than there are going into the negative. So there's like leftover lines. They just go off to infinity. But you see how, so if you were drawing that picture in the first place, the one in the middle of the page right now, and again, we're going to end on this, we'll probably end 2 minutes early. If you were drawing that picture from scratch, at first it seems like it'd be very hard to draw, maybe. But what you would do is you just start with the left-hand dot and say, okay, it's got a charge of like, 5 coulombs, let's say. And the other charge has sorry, the first charge is like +5 coulombs, and the other one is, let's say, like -4 coulombs, right? And that's what's given. So so you're going to draw like 40 lines coming out of the first one, but you're going to draw them as symmetrically and smoothly as possible. Like, so you draw a bunch of lines coming out in all radial directions from the first, and then you draw a bunch of lines coming in to the second one, all in a pattern in as much symmetry as possible. But then you'll notice you have leftover lines from the first one because it's more highly charged. So those leftover lines go off to infinity. They have nothing to connect to because they're not allowed to just stop in the middle of the page. And that's why you get a certain amount of asymmetry in the lines here. But there's no other way you could have drawn these as long as you're willing to draw, as long as you're willing to stick to your scaling factor and you're trying to be as patterned and as smooth as possible, and you're making sure that lines never spontaneously start or stop. Um, they always, if they're going to end, they end at a negative, and if they're going to start, they start at a positive. That's the picture you'd end up with. And again, what that picture is showing, we'll just end on this, is like if I were right here, if I were a positive test charge right here, I would be shoved to the right. How can I tell? Because the tangent line to the curve right there is pointing to the right. So I'd be shoved away from the left-hand positive charge toward the negative charge. I the I I wouldn't be shoved right. I wouldn't be shoved up or down because the vertical components cancel, and I'd be shoved with a weaker amount of force than I'd be shoved here or here or here. That's what it's saying. I think that's enough for right now. So I'll stop the share. Hopefully you get the point of how field lines work. We'll end on that, and then we'll go to the next topic, which is flux on Wednesday. But thank you for your patience. Oh, and I'll stop the recording. If there's any quick questions, I'll answer questions. But other than that, release the exams, the ones that I have like right now. But I'll stop the recording.